When a photon strikes a molecule, it scatters. The trajectory and energy of that scattered light contain precise physical information about its atomic bonds. Most of the time, this collision is elastic. The photon bounces off with its original energy completely intact, an event known as Rayleigh scattering. But a tiny fraction of these collisions are inelastic. The photon exchanges energy with the molecule's vibrations, shifting its wavelength. This is Raman scattering. Measuring that shifted wavelength gives us a unique chemical fingerprint of the target material. The physics, however, present a severe limitation. Inelastic scattering is exceedingly rare. Out of roughly 10 million incident photons, only one will produce a Raman shift. Consider a target analyte like crystal violet. In chemical and biological testing, identifying this molecule at trace concentrations is critical. Yet crystal violet produces an inherently weak Raman signal. If you attempt to detect trace amounts of it using a standard Raman spectrometer, the returning photons are so scarce that the chemical signature becomes indistinguishable from the baseline sensor noise. Extracting that signature requires a physical intervention before the light ever reaches the lens. We have to use surface-enhanced Raman scattering, or SERS. This technique forces the analyte to interact with a specialized substrate designed to actively amplify the returning signal. Massive signal amplification cannot be achieved by relying on a single physical mechanism. To extract a clear reading from near-zero concentrations, the substrate must simultaneously generate localized electromagnetic fields and optimize charge transfer pathways between the surface and the target molecule. To achieve this, researchers engineer a highly specific hybrid material, gold atoms stoked directly into a two-dimensional transition metal dichalcogenide known as molybdenum disulfide, or MOS2. By merging the intense optical reactivity of a plasmonic metal with the high surface area of a 2D semiconductor, the resulting substrate forces the target molecule into an environment where its vibrational signal is magnified by orders of magnitude. Before analyzing the signal, the substrate itself must be fabricated flawlessly. Traditional chemical synthesis methods typically leave behind trace precursors and chemical residues. In highly sensitive SERS, those surface impurities will interact with the laser and ruin the reading. The solution is nanosecond pulsed laser ablation in liquid. A high-energy laser directly irradiates a solid metal target submerged in a solvent, instantly fracturing the material into a cloud of suspended nanoparticles. This is a strict top-down approach. Because the nanoparticles are sheared directly from a pure solid, the process bypasses hazardous chemical precursors entirely, guaranteeing the high-purity surfaces required for trace detection. Generating the particles is only the first step. To verify that the material possesses the exact geometry needed to capture molecules, researchers must observationally confirm its crystal lattice structure. They verify this phase purity using X-ray diffraction, or XRD. Looking at this X-ray diffractogram of the ablated sample, we see sharp, distinct intensity peaks emerging at exactly 14.5, 33, 58.5, and 69.7 degrees. These specific diffraction angles map directly to the 002, 100, 110, and 201 crystallographic planes of a standard MOS2 hexagonal lattice. Because the graph displays sharp peaks with absolutely no extraneous spikes outside of this specific hexagonal signature, phase purity is confirmed. The laser ablation produced uncontaminated MOS2. With the lattice structure confirmed, the XRD data provides the parameters needed to calculate the exact physical size of the crystallites using the Scherer formula. This equation defines the crystallite size, d, as a function of the X-ray wavelength, lambda, divided by the line broadening at half the maximum intensity, beta, multiplied by the cosine of the Bragg angle, theta. Using the empirical data extracted from the laser-ablated sample, the variables are set. The X-ray wavelength is 0.154 nanometers, the beta value is 0.03136 degrees, and the theta angle is 16.56 degrees. Resolving the math yields an average crystallite size of approximately 265 nanometers. To corroborate this mathematical derivation, researchers imaged the exact same substrate under a field emission scanning electron microscope. This simulated micrograph demonstrates a uniform distribution of nanostructures across the surface. While the particles exhibit slight agglomeration, the physical grain size averages around 140 nanometers, validating the nanoscale morphology predicted by the math. The laser ablation clearly succeeds in producing pure, structurally verified MOS2 nanostructures. However, physical morphology is only a housing. The substrate still lacks the electronic engine required to dramatically amplify a Raman signal. Signal enhancement requires active sites that can exchange electrons with the target molecule. To create those sites, the intrinsic electronic structure of the MOS2 must be modified. Introducing gold dopants into the MOS2 lattice alters its conductivity and shifts its electronic bandgap. Researchers measure the extent of this electronic shift by analyzing the optical absorption of the samples using UV-vis spectroscopy. Here we see a Tauk plot, which translates the UV-vis absorption data to reveal the bandgap energy. The plot displays two distinct lines, the unprocessed MOS2 base and the new, laser-processed, gold-doped substrate. Evaluating the x-intercepts shows a clear shift. The bandgap energy increases from 2.01 electron volts in the raw state to 2.30 electron volts after the gold doping. This higher 2.30 electron volt bandgap aligns the energy levels of the substrate more closely with the molecular orbitals of foreign analytes, establishing a highly efficient bridge for charge transfer. With the geometry and the electronic structure locked in, the substrate is ready to exert two simultaneous physical effects on any molecule that lands on its surface. The first effect is strictly electromagnetic, driven by the gold nanoparticles. Look at this diagram. When the incoming Raman laser hits the gold, it excites the free electrons on the metal surface, causing them to oscillate in sync with the light. This creates an intense, localized electromagnetic field, known as localized surface plasmon resonance. This resonating plasmon acts like a microscopic optical antenna. It forcefully concentrates the light field exactly where the target molecule sits. The second effect is chemical, driven by the newly doped MOS2. The flat, two-dimensional planar structure of the MOS2 offers an exceptionally large surface area, highly optimized for molecular adsorption. It pulls the analyte molecule into direct physical contact with the lattice. Once docked, the chemical effect takes over. As shown in this energy diagram, the modified 2.30 electron volt bandgap acts as a corridor. Electrons flow rapidly from the conduction band of the MOS2 substrate directly into the energy states of the analyte. The extreme sensitivity of the substrate relies entirely on this synergy. The gold generates an intense localized optical field to illuminate the molecule, while the engineered MOS2 provides the physical bridge for rapid electron exchange, magnifying the vibrational scattering. To validate the physics of this dual mechanism, the AU-MOS2 substrate is tested against an analyte. Crystal violet is reintroduced, this time at extremely low trace concentrations. The dilute liquid is drop-casted directly onto the hybrid substrate, allowed to settle, and then placed under the focal point of a Raman microscope. This chart compares the resulting source spectra against a normal Raman reading of the exact same molecule. The difference is immediate. Where the normal reading shows practically a flat line, the AU-MOS2 substrate forces massive, sharply defined intensity peaks out of the trace sample. The highest recorded characteristic peak for crystal violet appears right here, at approximately 1615 inverse centimeters. Directly below it, at roughly 1620 inverse centimeters, is where the normal Raman peak should be. The standard method detects almost zero signal intensity. Furthermore, researchers observed that even as they systematically decreased the concentration of the crystal violet drops, the hybrid substrate continued to yield a clear, highly detectable Raman signal. To evaluate the true efficiency of the substrate, this disparity in peak intensity requires rigorous quantification. This is calculated using the enhancement factor, or EF, which directly compares the signal intensity generated per molecule on the SIRS substrate against the normal Raman baseline. The calculation resolves to a final magnitude between 10 to the third and 10 to the fourth power. In practical terms, the hybrid material amplifies a previously invisible chemical signature by up to 10,000 times. Standard Raman spectroscopy fails at trace detection because the rate of inelastic scattering is inherently weak. By executing a top-down, pure laser synthesis and combining the plasmonic resonance of gold with the engineered bandgap of a 2D semiconductor, researchers created a substrate that physically compensates for that weakness, bypassing an insurmountable barrier in chemical trace detection entirely.